Okay, let's begin. So, in the last class, we kind of looked at what negative feedback does to nonlinearity. So, we essentially noticed that even though the system or the amplifier you make is nonlinear, the moment you enclose it in a negative feedback loop like this, something I'll draw it quickly, then at the output the nonlinearity is reduced, right? And that essentially happened because as long as you have a large enough loop gain, the error signal here is going to be small. So which means although your actual input signal will be swinging so much, the actual signal that excites the nonlinear system is going to be very small. So it's going to behave more linearly, right? And to be more technically right, we saw in the last class the negative feedback loop generates this error signal. And how is this error signal related to the input signal? If this has a nonlinearity f, it was related to the inverse nonlinearity. So that is why when you actually follow it up with the actual nonlinear system, it kind of cancels, right? Great. And yeah, as I mentioned, this is a normal thing that we typically use to counter nonlinearity. If you find something to be nonlinear, one way to counter the nonlinearity is you somehow estimate this nonlinear function, put an inverse nonlinearity before or after this to counter it, and when you use a negative feedback, it kind of does it free for you. And we also saw the method of current injection that helps us compute the nonlinear coefficients for weak nonlinear systems. So you know the output, you typically have a linear portion, a second order nonlinear portion, a third order nonlinear portion, and so on. As long as the first order term is greater than the second, which is in turn greater than third, and so on, that is what we call as weak nonlinearity. So if you have some circuit, so let us say take some signal V in, you have a whole bunch of things, and let us say you have some nonlinear block, and let us say it is some GM. So let us say this current is some GM times Vx plus GM2 Vx square plus so on, and you have some more things and you get V out, right? So the basic idea is you first assume that the nonlinear element is actually linear. So it is only generating the linear portion of the current. The nonlinear portion is an additional current that is getting added. So let me write it here. So this is the nonlinear current that is added. Let us say it is some GM2 Vx square and so on. So the first step is now the circuit kind of becomes linear. So we can treat it as having two different inputs and use superposition. So first step, you assume that the input is 0 and you find what V out is. That gives the linear portion of the V out. Similarly, you find what is Vx, that is the linear portion. Vx is basically the signal exciting the nonlinearity, right? So once that is done, you find the response due to the second current source. So again, ideally you should know the entire information about Vx, but right now you just know the linear portion, so you approximate Vx to be the linear portion, and then you say my injected signal is this Vx linear portion square plus GM3 cube and so on. So right now we have found the linear portion. To find the second order nonlinear portion, you choose an appropriate term here that gives you the second order term and assume that alone as the input, and then find V out 2. Now then using V out 2 you find V out 3 and you can keep doing it, right? So that's the idea. Cool. So now let me ask you this. So let us say I have a differential amplifier with a tail current source. Say this is V1, V2. Now let us say I am interested to find the nonlinear relation between the differential current versus the differential input. Again, I asked you to work out, you can check it later, but we kind of qualitatively saw how the characteristics is going to look like. So let us say this is V1 minus V2, and here I plot I1 minus I2. So how is this going to look like? For small signals, how is it going to be? It's linear. And if I keep increasing the differential input, what happens? After some point it saturates to I0. In the other side it saturates to minus I0. So on top of this, if I plot the short circuit GM is essentially the derivative of this, right? That's all. So if I plot the derivative of this guy, how do you think that will look like? Again, for small signals, what can you say about GM? It's constant, so it will be some value. And as my input increases, what can you say? I mean, I'm taking the derivative of this curve, that's all. There is nothing significant I'm doing, right? It's going to drop, right? Something. And as we already remarked, this is basically a compressive nonlinearity. That is, if I increase the input, the short circuit GM is also dropping after some point, right? So this is something we already noted. Now let me take a differential pair, but without the tail current source. So it's a pseudo differential pair. Again, I try to do the same experiment. I try to plot the differential current I1 minus I2 versus the differential input V1 minus V2. So can you help me sketch it now? Let us say V1 minus V2. Again, for small signals, what can you say? It's going to be linear. That point, I think there is no confusion. Wait, let me something. Now, if I keep increasing the differential input, in the earlier case, my current got saturated to a constant I0, that is the tail current source. Here, let us say I keep increasing V1. What can you say about the differential current? That will also keep increasing, right? And after it comes out of the within quote small signal region, what can you say about the relation between current and voltage? It's going to be a square law, right? So first order, so square law, so it's basically do something like this, right? This fine. So once again, here if I try to plot the short circuit GM, which is essentially the derivative of this with respect to the voltage. So how do you think that will look like? Initially it's constant, and then yeah, okay, it's going to increase, right? Something. So this is basically what we call as an expanding nonlinearity. Cool. So that's essentially what I wanted to discuss about nonlinearity. So now at this stage, you guys know how to design op-amps. You also know what are the possible non-idealities you can encounter while designing these things, and you know how to tackle them. So let us say you go and make an op-amp. So let us say this is the first stage. This is the first stage GM, and let us say the second stage is a common source. Say it's a PMOS input common source like this, biased with a current source like this, right? And let's say I want to drive a resistive load, so I go and put a load resistor RL. Again, notice that I will not connect this to ground. I will connect it to the common mode so that the DC bias is not disturbed, but I will not show it explicitly to avoid clutter. Cool. So here let us say my input here reduces, that is the gate here reduces. What can you say about the output? That will increase with some amplified factor, something. So here if the gate increases, this will decrease, right? Again, I'm not showing the full picture. Assume it's put in some negative feedback and this is happening. Okay. So ideally, let us say I want to have as large a swing as possible at the output. Make sense? And also I want to drive a small load resistor also. If that is the case, what can you say about the current that needs to be sunk and sourced out of the resistor? If the output swings are large and the resistor is also small, the current that needs to be pushed and pulled will also be large, right? Now, when the signal is going low here, which means the output is trying to go higher and higher. If the signal is going low here, the gate voltage for the PMOS reduces. So what can you say about the current? That will increase. So the PMOS will push in more and more current into the load resistor and it can keep increasing the output. No worries. Right? Now on the other side, let us say it's try to increase here. So the output needs to drop. When the output has to drop, the current has to be sunk from the load resistor. Right? That's when the output is going to drop incrementally. So what is the maximum current do you think I can pull out of the resistor? It's limited by the current source I2. Fine. So I'll just write here the maximum load current I can deliver is I2. Right? Because you want to make symmetric. You want to maintain symmetry. So this kind of setup is called a class A bias or a class A stage, wherein you have bias the stage with a constant current, right? So here, as you see, there is no issues when the output wants to go higher and higher, right? When the output is trying to go higher and higher, the gate is also going lower and lower. So this can nicely sink in more current, but sorry, this can nicely source in a lot of current, but you are limited on the other side, right? But that is not ideally you want. That's not ideally something you want, because you want to make sure that you are able to drive as much current as possible to the load, right? And also, as you can see here, this is not that great with respect to power efficiency, because you're always drawing a current I2 with respect to the bias point, with respect to the bias picture, irrespective of the current required by the load, right? So I'll just say that not great power efficiency. That is, if you take the power that you are actually putting out into the load divided by the power you are consuming for biasing, that is very small. Okay. Now if you have, this is with respect to a PMOS stage. Now if you have an NMOS stage, you will have the reverse problem. You will be able to sink in as much current as possible, but while sourcing you will have limitation, right? So that's issue with the class A stage. But as I mentioned, you want to make sure that you can deliver, that is, you can source and sink as much current as possible based on the load resistor. Now you see PMOS has no problem in sourcing current, NMOS has no problem sinking current. So what can you do? You can combine the two. So let me actually make some space. So that gives rise to this structure. So you have, I'll not show the first stage, I'll show only the output stage. So if you have a PMOS and connected to the load, this can source any amount of current depending on the load resistor. I have an NMOS that can sink any amount of the current. So I'll use both in parallel. And ideally the small signal must also be fed to both of them like this. Right? So here once again, if you do the same thing, let us say the input reduces here, the output increases, here it increases, it falls. So here when the gate voltage reduces, the NMOS will stop responding, right? That is, let us say the gate voltage is dropping smaller and smaller so that the output can increase larger and larger. Let's not worry about whether the transistor is in saturation or not. Let's just see what is the maximum you can reach at the output, right? So if the output is trying to reach higher and higher, the gate will also drop lower and lower, and finally the NMOS will stop responding. The PMOS will nicely respond. It will source as much current as required by the load resistor. And what is the maximum the voltage here can reach now without worrying region of operation of transistor? It can reach as close, it can reach VDD here. Right? Let's not worry about it is in saturation or not. Let's just see what is the maximum, absolute maximum I can go. Fine. Similarly, if the output is trying to go lower and lower, which means the input here will try to go higher and higher. After some point, the PMOS will stop responding. The NMOS will take charge. It will nicely sink the required current, and the output here can go to 0. Fine. So this kind of stage is called as a push-pull stage for obvious reasons, because it can push and pull current to and from the load, and this is called class AB stage. You don't ask me why it's called class A, I have no reason. Someone decided to name it like that. So, and another nice thing here is, here I can make sure that when the small signal is not there, the bias current in the transistor is not so much. So I can keep the quiescent current to be small here. Right? So which means as and when the output is required to go high or low, the transistors will sink or source the required amount of current. Right? You try to keep the quiescent current small, so that depending on the signal swings here, the transistors will sink or source the required amount of current. So that way it is very good for power efficiency also, because you are not consuming a lot of current unnecessarily. Depending on the current requirement from the load, your current consumption also changes. Is that okay? But of course nothing comes for free. Now the issue is, see here, if the output has to go higher and higher, as we saw at some point, this guy will go off. So which means transistors are going in and out of saturation. So what is the issue? Sorry? No discontinuous. It's non-linear, right? It is going in and out of saturation, so it's going to be more non-linear, right? But typically it is okay, because as we saw, finally this is going to be used in negative feedback. So as long as you have sufficient gain coming from the op amp, you'll have some stages before, right? Let's say 2 stages before, and that is giving a lot of gain. As long as you have a lot of gain, finally when you are using it in negative feedback, the negative feedback will reduce the non-linearity. So that's why typically it is okay, as long as you make sure that the gain is higher. So non-linearity is an issue here, but of course with negative feedback it is fine. So maybe I'll not write it. And as we saw, the output can reach 0 on one end, VDD on the other end. So this is what we typically call as rail to rail swing. Cool. So now you know that this is non-linear. Can you tell me whether this is a compressive non-linearity like this or an expanding non-linearity like this? Yeah, why expanding? Yeah, as you're pointing out, if you keep increasing VI, the current is not limited, right? Depending on the required input, one of the transistors will take charge and the current will keep increasing. So it's kind of an expanding non-linearity, and that's what you typically want. You don't want your current to be limited. Depending on the load, you push in as much current as possible. Okay. So typically for driving small resistive loads, class AB stage is what is typically preferred at the output. But arranging it as such like this has some issues. So let's look at that. So let me draw this again. So the idea is I want to have both NMOS and PMOS acting simultaneously. So let us say I have the load resistor here. So we wanted to connect it like this, and remember this will be connected from a previous stage, right? And ideally we want to make sure the small signal is applied to both these guys, right? But remember that the bias from the previous stage might be compatible with only one of the transistors typically. We already saw while designing two-stage op amps. So let us say the voltage coming from the first stage is only compatible with PMOS. So which means I can't go and connect it directly, right? So let us say here the voltage is compatible with PMOS, so I can connect to the PMOS directly. But for the NMOS I can't use the same voltage. So let us say I get some other bias voltage VBN. Okay. But I want to make sure that the small signal Vin is directly added here, right? So the final voltage I should get here should be the required bias for the NMOS plus the entire small signal. So now you tell me, I have this bias voltage, I have this signal. How do I combine these two and feed it here? In the first analog circuits course, how do you bias transistors? I have the required bias voltage here. I want to make sure the bias adds here and the small signal adds here. Tell me something. I mean, I know the voltage, I don't need to generate voltage. Let us say the voltage is known. Okay, from Vin, capacitor, and what about VBN? If I connect it directly, this voltage is what now? It's just VBN, right? You can't connect it directly. So what do you connect? Huh? Okay, let's not go to inductor. Something else? Have you not seen this? I mean, if I do this, see, let's try to solve it, right? I mean, I have two inputs. Let us say I short this guy. What will be the voltage here? I apply VBN. It's an RC circuit. I have a DC VBN applied. So what will be the DC here? It will be VBN, right? Remember, I mean, these two voltages have to be equal, else there will be some DC current flowing. If DC current flows through capacitor, the voltage will keep increasing. So steady state is reached only when these two voltages are equal. Bias is set. So what about the small signal? Let's look at small signal. With respect to small signal, I have Vin given to a capacitor and a resistor, right? So if I write in Laplace, what is V out of S? Huh? I mean, it's not, yeah, it's voltage division. So we just plus 1 by SC. So this becomes SRC by 1 plus SRC times Vin. So, but you want this to be equal to what? Vin. So what you should ensure? The omega RC is much greater than. So RC should be greater than the minimum frequency you have for your input, right? So typically this having a large RC constant is ensured by having a large resistor here, okay? And again, see, remember that if your frequency is low, even this RC product will have to be really large. So ideally speaking, you can't have a physical resistor that is very large, because that's going to take up a lot of area. Let us say you want to make some tens of giga ohms of resistor. It's not physically possible to have such a large resistor on chip, right? So can you tell me something else which can emulate a large resistor? Huh? Sorry? How do you use transistor? If you diode connected, it's a small resistance, right? I want to have an incremental very large resistor. I mean, what is something that can mimic a very large resistor? Huh? Voltage buffer meaning? No, remember that if you have I need to also make sure current flows. If you have voltage buffer, the input resistance is infinity, you are right, but no current flows. I mean, if you have a what is CS? No, I just need to get two terminal element, right? I mean, if you have a switch which is open, what is the resistance? That's what we typically use. So typically there are multiple ways in which this can be done. One way is to take a MOSFET and have it in off state. Okay, so again there are multiple variants, you can do anything. Just make sure that the MOSFET is off, and then it mimics a reverse bias diode. Okay, so this is typically called a pseudo resistor. It's not an actual resistor, it's kind of a resistor though. With this you can easily get giga ohms of or tera ohms of resistance also. And in fact, I mean, there are people still trying to get better and better pseudo resistors, because it turns out in this biomedical applications, the signals you are dealing with are really small, let's say a few tens of hertz or maximum 100 hertz or something, right? So there once again you need to make sure the R is very large, because see there again you want to make an amplifier, and typically it is not diode connected. Basically here this is connected. So basically if you look at the structure, it will look like a off diode. Okay, I will not go into details. You can draw the structure of an NMOS, P, NP and stuff, and then see it will mimic like a reverse bias diode. That's all. Right. And as mentioned, typically it's required because one simple way to make an amplifier is this, an inverting amplifier, to get an accurate gain. But if you use a resistor here, the resistor is going to generate noise. So what else can I use to get an inverting amplifier? I mean, yeah, let's say you want to get an accurate gain, you have an op amp, you can make an inverting amplifier using resistors. The gain is the ratio of the resistors, it's well controlled, but adding resistor is going to introduce noise. So instead of using two resistors here, what else can I use? Sorry? Slower, what? No, I mean, that is also the same thing, right? I mean, pseudo resistor is going to be large, right? Yeah. You can use a capacitor, right? This also typically works. Same thing, it's ratio of capacitors. Okay, but with small signals it is fine, but is there a feedback at DC here? A DC capacitor is opened, the op amp will not have a DC negative feedback, so which means the bias points will not be set, things will not work. So you need to have a DC negative feedback, so that's where typically you try to have a very large resistor here. You have a very large resistor so that it doesn't, when these two are in parallel, this doesn't come into picture, but at DC that provides a feedback. So that's where these pseudo resistors are commonly used, one of the places. But anyways, coming to the point, yeah, to make sure that the NMOS here has a different bias voltage, you do this RC coupling that you learnt in your analog circuits course, and do this. And one way in which you can get this bias voltage is also, I'll show once. So let me draw a simple diff amp as a first stage. So let us say this is the first stage, and the final stage is class AB stage. So I mean, I'll just draw from one side, whatever I draw here will come on this side also, right? Fully differential. So here let us say to the PMOS I connected directly. Right. Now I need to generate a bias voltage that is compatible for the NMOS. Now can you look at the circuit and tell me, is there some other point that also has similar voltage that is required by this guy? This guy, right? Remember, we need to have a gate to source voltage. Anyways, we are going to bias the current source with a particular VGS. We can kind of match the two transistors and reuse the same thing. So one way is you can actually put the pseudo resistor here, whatever, and then have the capacitor here. This is the, so this is one way in which you can do class AB biasing. But yeah, I mean, issues now again, if you are looking at very low frequencies, the resistor required will also be really large. So let us say that is not something that you can work with. There are other ways in which you can bias this two transistors. I'll just show one technique. So let me look at the problem once again. So the problem is this. I have, let us say, bias voltage I get from the previous stage is compatible with the PMOS transistor. For the NMOS transistor, I need to have some other voltage. So let us say that voltage is some VBP plus Vin minus some V0. So what is something I can put between these two so that this voltage is of the required value? Sorry? Yeah, I mean, exactly, right? So let me, what he's saying is, if this, let us say, if this was VBN plus Vin, so he is suggesting we'll put this guy VBN minus, sorry, if you have a DC voltage source of appropriate value, that's going to level shift the DC alone, right? With respect to small signals, what can you say about the voltage source? Short. So the small signal Vin is directly going to come here and the DC level shifting is happening. Okay. So in principle, if you have what is called as a floating battery, yes, I'm calling it floating battery because both the positive and the negative terminals of this battery are accessible to you, right? Typically all voltage, I mean DC sources, the negative is grounded. You don't have access to the negative terminal, but in this application we need to have something like this. So we don't have a real voltage source like this. So can you think of some way in which I can get a voltage drop across 2 points? Let me draw this once again. So all I want is a DC voltage drop across these 2 points. What is something I can use to get a voltage drop? Resistor, and push a current through a resistor that gives voltage drop. Simple. So I need to put a resistor here. Okay, fine. And make sure I pass an appropriate current here. So if this is some I, the drop is IR. So again, this is fine, but there are two issues. First is that remember that this NMOS transistor will have process variation. So from chip to chip there is going to be variation in the properties of this, but the resistor here will not be able to track the variations there because it will have its own variations, right? So remember that if you have two identical things, they will match on chip. If you have two different elements, you can't expect them to track each other. Okay, so that is one thing. So which means this is not robust. And the second issue, or let's focus on the first issue itself. The first issue is because you are trying to get this voltage drop for an NMOS transistor, but that is being done by a different kind of element. Fine. So what could be a solution for that? If I don't want to be or if I want to be immune to this variation, that is, if I were to be able to track variations in this transistor, I obviously cannot be using a resistor to generate the voltage drop. What should I use? I should use another transistor. So I should use, let us say, an NMOS transistor. How can I get a voltage drop using an NMOS transistor? Remember, this has to be a DC drop. It should be relatively constant DC voltage drop. Can you think of a way in which I can get a relatively constant voltage drop across transistors? I have a current source here, so think about it. Correct. Okay. So how do you propose somewhere? I mean, across which two terminals I should look at? So let us say this is in saturation and I have a current I0. What can you say about VGS? It's some constant. So I can get a voltage drop between gate and source. Fine. That's what he suggested. So which means I'll basically put a MOSFET, let us say connect it to some Vx, we'll see how we can generate that voltage. Then this voltage will be Vx minus the required VGS at the particular current I. Okay. So this is fine with respect to the DC picture. Now, but the issue is, see here if I have a small signal V in, the gate voltage for the NMOS should be equal to that V in. That's what you want, right? But here if you see what's happening in small signals, so if I draw the small signal alone, I have, let us say this is some MA, I have the transistor MA here, gate is incrementally short, drain is where I have the small signal input V in, right? And here I have a current source, let us say the current source has some output resistance R0, right? And this is the gate voltage. Assume that this transistor has infinite R0 to simplify, or let's say you can consider R0. So this is the case. What can you say about VGN in terms of V in? Does it resemble you of something that you have already seen? Huh? It's a cascode. So what is this voltage here with respect to this? Or how will you find? So what is he looking in resistance? Huh? It's GM R0 times this. So the small signal current is what? If I apply voltage V in by the, let us say GM A R0 A times R0, that current is flowing here. So what is VGN? So this voltage times, I mean this current times R0 gives that voltage, so that's going to be, so R0 by this guy. So this is, I mean this is something you already saw with cascode also, right? I mean that is why the cascode is good, because if there is any changes in the drain voltage here, this is another transistor, this drain voltage is not changing so much. That is why this is becoming a better current source. Remember cascode, the idea was you take this current source, put a current buffer, right? So anyway, so now you see if I apply V in, I get this as the gate voltage. Is it good or bad? Huh? That's not something you want. You ideally want the entire V in to appear here, but you see only a small portion of V in is appearing. In fact, this was the problem with the resistor also, right? You will have same issue here. Okay, and this is happening because remember ideally what we want was this. So with respect to small signals, what do you want the resistance here? 0. With respect to small signals, you want the resistance looking in between these two terminals to be 0, as small as possible. But now that is not small because you have gone and connected the drain of the transistor. So which means this will be very high impedance, right? And that's what is causing the issue. So to reduce the impedance, I should connect something here, right? And that should reduce the impedance. And preferably, I mean, I don't want to use a resistor because I want to track things. So I might want to use a transistor. So what terminal of the transistor I can connect here so that the resistance reduces? Can connect a source. So somewhere source should come. So drain should come here. Current is flowing in this direction. I should use PMOS. So which means I'll go and do, let us say this is connected to some voltage VY. We'll see how we can generate it later. Okay. So now we can see what's happening to the small signal thing. Let me erase this. So now I have a PMOS in parallel. Fine. So now, okay. So let's find VGN now. Ignore the output resistance of this MA/MB. So if that is the case, what can you say about the current in this direction, I1? The current through the transistor MA, what is the incremental current? Why? Yeah, it's GM VGS, right? What is the current in the direction? GM VGN, right? What is the current in this direction if I call it I2? GMB times Vin. So what is the current flowing here? Current flowing into the current flowing in the downwards direction is difference between the two currents. That is how much? GMB Vin. So this times R0 is, right? So you simplify, VGN will be what? GMB R0 V1 plus GMAR. Now again, if I keep GM of the two NMOS and PMOS to be roughly same, and GM R0 if it's greater than 1, then this is as good as P. Right? So if you find the small signal resistance between these two, it's going to be of the order of 1 by GM. So that's why you get a small resistance here. Okay. So again, one last point here is how do you generate this voltage Vx/Py? It's pretty straightforward. See, the voltage Vx, it is basically supposed to be 1 VGS plus 1 more VGS, right? Basically, I need to have 2 VGS drops, right? Let us say I have the two transistors to be matched. So, which means I need to have 2 VGS drops. How can I generate a voltage which is 2 VGS dropped? I can have? Yeah, if you have diode connected stuff, let me. So, if you have, let's say you mirror the same current here and then do 2 diode connections. This voltage is VGS, this is 1 VGS, which means this will be 2 VGS. So as long as you make sure that the NMOS transistors are all matched and similar, this will nicely work. So this you can go and connect it to Vx. Right. Now look at Vy. Vy is basically VDD minus 1 source to gate drop minus 1 more source to gate drop. So how can I generate? I'll do the same thing with the PMOS, right? So I'll have 2 PMOS transistors and mirror the same current here. Once again, I need to ensure the PMOS transistors are all kind of matched. Okay. So this is one nice way in which you can get the voltage drop, DC voltage drop across the 2 gates, but ensure that the small signal is kind of a short, right? So this is typically called the Monti-Celli bias or Monti-Celli stage, named after Monti-Celli, who came up with this. So this again one variant typically is used if you want to do this class AB biasing. Okay. So bottom line is, if you want to drive resistive load and if you want to get maximum swings, that is if you want to get rail to rail swings from 0 to VDD, you use a class AB for the output stage. That essentially means you use both NMOS and PMOS for amplification without fixing a tail current, without fixing the bias current to a constant. And in a class AB stage, you need to make sure the NMOS and PMOS have appropriate bias voltages, and that you could either do using this floating battery arrangement, or you can do this, RC coupling, wherever it was. Yeah, this kind of RC coupling or the floating battery, something you can use. Cool.